On October 19, 2017, a telescope on Haleakala detected something that, by the rules of orbital mechanics, should not have been where it was. The object was moving too fast. Its trajectory was hyperbolic, meaning it was not bound to the Sun. It had come from outside the solar system, and it was leaving. Within weeks, astronomers confirmed it as the first interstellar object ever observed in our system. They named it Oumuamua, Hawaiian for Scout. But Oumuamua did not behave like any asteroid or comet on record. As it receded from the Sun, it accelerated, and no telescope on Earth or in orbit could find the gas trail that normally explains that kind of acceleration. That single gap, between the observed push and the absence of visible outgassing, is where the facts stop making clean sense, and where a Harvard department chair decided the most plausible explanation was that Oumuamua was not a rock at all. To understand why a distinguished astrophysicist would stake his reputation on that claim, you have to understand the systems that produced the data. The Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, was designed to catalog near-Earth objects. It was not built to catch interstellar visitors. Oumuamua appeared as a faint point of light, already on its way out, already past perihelion. The astronomical community had roughly 3 months of observation before the object faded beyond detection. Every conclusion drawn about Oumuamua rests on that narrow window, and on the assumptions baked into the models used to interpret limited photometric data. Before reconstructing what happened, you need a clear picture of what the evidence actually establishes, and what it does not. Tier 1 evidence in this case includes the orbital data from multiple independent observatories confirming the hyperbolic trajectory with an eccentricity of 1.2, the documented non-gravitational acceleration published in the peer-reviewed Nature paper by Mihilai and colleagues in 2018, and the photometric light curve showing large brightness variations. Tier 1 also includes the negative results. The Spitzer Space Telescope observed Oumuamua's position and detected nothing, placing an upper limit on any dust or gas emission far below what a typical comet produces. The Hubble Space Telescope tracked the trajectory and confirmed the anomalous acceleration persisted. Tier 2 evidence includes the convergent assessments of multiple independent modeling teams regarding the object's shape and reflectivity, though these carry more uncertainty than the raw orbital data. Tier 3 includes single-source interpretive claims, such as the specific geometric models proposing a pancake or cigar shape, and AVI-Lub's argument that radiation pressure on a thin sail structure explains the acceleration. Not evidence includes the etymology of the name, internet speculation, and pattern matching to science fiction narratives, all of which have clouded public discussion of this case. 2 logical rules apply throughout. Correlation does not equal causation. An observed acceleration consistent with radiation pressure does not prove radiation pressure is the cause unless the mechanism is demonstrated. An absence of evidence is not evidence of absence. The failure to detect outgassing does not prove there was none, only that none was detected within instrumental limits. With these tiers established, 3 specific anomalies emerge that the standard scientific record struggles to account for. First, the non-gravitational acceleration without detected outgassing. The official record cannot account for this because the magnitude of acceleration observed would require a level of mass loss that, for any known comet composition, should have produced a visible coma or dust tail. None was detected despite observations across multiple wavelengths by instruments capable of detecting such emissions. Second, the extreme shape inferred from the light curve. The object's brightness varied by a factor of 10 as it tumbled, suggesting an elongation ratio of at least 5:1, and possibly 10:1. No known asteroid or comet in our solar system has been observed with this aspect ratio. The official record cannot account for this because it has no documented analog. Third, the object's apparent high albedo and small size. The reflectivity inferred from the photometric data suggested Oumuamua was unusually reflective relative to typical solar system bodies, and relatively small, on the order of 100 meters in its longest dimension. The official record cannot account for the combination of these properties in a single natural object, because we have no precedent for an interstellar fragment that is simultaneously extremely elongated, highly reflective, and small enough that radiation pressure becomes dynamically relevant. Now consider what the evidence establishes with confidence. The evidence establishes that Oumuamua was an interstellar object on an unbound hyperbolic trajectory. It establishes that the object exhibited non-gravitational acceleration as it receded from the Sun. It establishes that no coma or dust emission was detected despite sensitive observations. It establishes that the light curve implies an extreme shape unlike any body previously catalogued. It does not establish that Oumuamua was artificial. It does not establish that it was a light sail. It does not establish its exact composition, shape, or origin. These remain unknown, and any honest account must place them in that category. The event itself unfolded fast. On October 18, 2017, Pan-STARRS captured the object. Within 48 hours, follow-up observations from other telescopes confirmed its unusual orbit. By October 25, the Minor Planet Center issued a circular announcing the discovery. Cometary activity was initially suspected, and the object was provisionally designated as a comet. But as observations accumulated, no coma appeared. The designation was changed to asteroid. On November 20, the name Oumuamua was officially adopted. By late December, the object was too faint for most ground-based telescopes. The Hubble Space Telescope continued tracking into 2018. The Mihaly paper, published in June 2018, dropped the second surprise, the non-gravitational acceleration. At this point, the scientific community faced a problem. The acceleration suggested cometary outgassing. The absence of a coma contradicted it. Something had to give. The mainstream scientific response was to search for natural mechanisms that could reconcile the anomaly. Several hypotheses emerged. One proposed that Oumuamua was a fragment of a Pluto-like body from another star system, composed primarily of solid nitrogen. Desch and Jackson published a paper in 2021 arguing that an exo-Pluto surface could produce nitrogen ice fragments with the right albedo and that sublimation of nitrogen ice at the levels required might be below the detection threshold of the instruments used. Another model, from Seligman and Laughlin, proposed a hydrogen iceberg, a body composed of solid molecular hydrogen that would sublimate in the sun's warmth and produce thrust from a transparent, undetectable gas. A third model suggested the object was a loosely bound aggregate of dust, a so-called fractal structure, which could explain both the odd shape and the low mass relative to its apparent size. Each of these models accounts for some of the baseline facts. The nitrogen fragment model explains the high albedo and provides a potential outgassing mechanism. The hydrogen iceberg model explains the undetectable outgassing, since hydrogen does not scatter visible light. The fractal dust model explains the extreme shape as a consequence of low internal cohesion. But each model also carries significant gaps. The nitrogen fragment model requires a specific origin story, the ejection of a chunk of another star system's Pluto, that is plausible but unverifiable. It also requires that the sublimation rate be precisely tuned to produce the observed acceleration while remaining below the Spitzer detection limit. The hydrogen iceberg model faces a more fundamental problem: solid hydrogen sublimates extremely rapidly in interstellar space due to background radiation. A hydrogen iceberg large enough to survive the journey from another star system would need to have started implausibly large, and no known formation mechanism produces such objects. The fractal dust model, while elegant, struggles to explain how such a fragile structure could survive the intense solar heating at perihelion, which brought Oumuamua within 0.25 astronomical units of the Sun. The mainstream position, articulated most clearly by the International Astronomical Union and the bulk of the planetary science community, is that Oumuamua was a natural object, most likely a fragment of an exoplanet, and that its unusual properties reflect our ignorance of interstellar object populations rather than anything artificial. The implicit argument is that we have a sample size of 2 interstellar objects, Oumuamua and the later discovered Borisov, and that drawing sweeping conclusions from a sample of one anomaly is premature. This is the simplest explanation in the sense that it requires no new physics and no new entities beyond what we already know exists: planets, comets, ejection mechanisms, and the vast diversity of other star systems. AVI-Lub's competing explanation must be evaluated against this baseline. In 2018, Lub and his postdoc Shmuel Bialy published a paper in the astrophysical journal Letters arguing that the non-gravitational acceleration could be explained by radiation pressure on a thin, flat, highly reflective object, effectively, a light sail. They showed that the magnitude of the observed acceleration was consistent with radiation pressure acting on an object with a very high area-to-mass ratio. They noted that no outgassing need be invoked, and that the high albedo and extreme shape followed naturally from the sail geometry. They further observed that such an object could, in principle, be directed intentionally, though they did not claim evidence for directed motion. The paper was legitimate science. It proposed a specific mechanism, derived quantitative predictions, and published them in a peer-reviewed journal. But it also carried an extraordinary implication. If Oumuamua was a light sail, then it was manufactured. The evidence supporting this hypothesis is the set of anomalies themselves, the acceleration without outgassing, the inferred shape, and the high albedo. These are real. The question is whether they uniquely support the light sail explanation. They do not. The same anomalies are also consistent with the nitrogen fragment model, the hydrogen iceberg model, and potentially with natural mechanisms not yet proposed. The light sail hypothesis explains the baseline facts plus the anomalies with a single mechanism, radiation pressure, which is elegant. But it introduces a new entity of extraordinary complexity, an artificial interstellar craft, without direct evidence for that entity. It requires that an alien civilization built and launched a light sail that happened to pass through our solar system at detectable proximity during the brief window in which human telescopes were capable of observing it. The prior probability of this conjunction is extremely low, not impossible, but low enough that the evidence must be correspondingly strong to overcome it. The strongest evidence against the light sail hypothesis is negative. No radio emissions were detected from Oumuamua, no maneuvering was observed, and no artificial signals were identified despite targeted observations. Lub has argued that a defunct sail, tumbling and silent, would produce none of these signatures, and he is correct. But this makes the hypothesis unfalsifiable with the available data. A silent, tumbling sail is indistinguishable from an unusual natural object with the same photometric and kinematic properties. The hypothesis does not generate unique, testable predictions that distinguish it from the natural alternatives, given the observations we have. Now you must decide for yourself how to weigh these possibilities. The question is not whether Lub's hypothesis is possible. It is. The question is whether the evidence warrants it as the most probable explanation, or whether it remains one possibility among several, supported by anomaly but not distinguished by evidence. 3 open questions remain. First, what was Oumuamua made of? This would be resolved by spectroscopic data in multiple wavelengths, which does not exist because the object was observed too briefly and too late. The Spitzer non-detection constrains some compositions but does not identify one. Second, what is the population of interstellar objects? This would be resolved by discovering more of them, which is beginning to happen. The Vera Rubin Observatory, when operational, is expected to detect multiple interstellar objects per year. Each new object tests whether Oumuamua's properties are typical or genuinely anomalous. Third, could we ever catch up to Oumuamua? Several mission concepts have been proposed, including a solar sail chase vehicle. None are funded. The object is currently beyond Saturn's orbit and receding. Without a dedicated mission, we will never observe it again. The case of Oumuamua resists resolution because the evidence is permanent but incomplete. The observations are fixed. They cannot be repeated. The object is gone. What remains is a set of measurements that do not fit cleanly into any existing category, and a set of explanations that each account for some of the data while leaving other parts unexplained. Lubb saw in that gap the signature of intelligence. The mainstream saw the signature of ignorance. Both may be right. The honest conclusion is that we do not know what Oumuamua was, and that the evidence, as it stands, does not compel any single explanation. That is not a failure of science. It is a description of the boundary between what the data can establish and what it cannot. That boundary is real, and acknowledging it is the only position that respects the evidence.